Just about there, folks. It's official. Looks like we can get started. Welcome back, everyone. Excuse me. Well, we got through our first exam, so congratulations, folks. That's usually one of the more stressful parts of the class, getting just across the very first exam. As far as the grading goes on this, I tend to start grading on Friday. I'm hoping to complete it by Friday, but it's a pretty large class, so it might spill over to Saturday, possibly Sunday at the very latest. So however it lands on when the grading's completed, what I'm going to do is after I complete the grades, I'm going to go to the announcements forums and just make a post. Grades are available in Moodle. So that way you won't have to feel the need to come up here and check it multiple times. You can, if you like, just wait for that email to come through in your ISU email account. Then for the folks who are in the in-person section, the exams will be, let me get this to the right spot. There we go. Exams will be just returned to you as a hard copy. And for the folks who are on the fully online section, I'll be returning your exams by email, just kind of like how I do with your homework. So we'll pretty much just be repeating this exact pattern that we see in Moodle as we go through the weeks. So with what's going on going forward, we've got, let's see, several weeks where we're just covering content. We'll be in chapter 8, chapter 9, potentially right around here, we might get into chapter 11, but we're not going to be too far into it. That means right around between this weekend and this weekend, we'll be updating this right here to say the exact definite coverage on exam 2, provide the sample review problems like before, and so on. So the whole Moodle website is just going to repeat in that same exact pattern as we go throughout the weeks. Well, any questions at all, folks, so far about the exam or otherwise? Okay. Also with the exam, you might have noticed when you look at the front sheet, there were really two scores. One is going to be your exam score as a fraction. In Moodle, it's going to be converted to a decimal score. The other one's your course score. This is the reason it takes a little bit while to grade the exams. What I want to do is get caught up on all grading for the homework assignments. Then when I give you your course score on your exam, that's going to be your standing in the class as of pretty much Friday of this week, the 20th. It'll take into account all of your homeworks that were due, as well as your exam 1 score. It just give you a total score as you are so far. And we'll be doing that with each one of the exams. So with what we've got going on so far, we're still in section 7.8. This is a pretty large section. So if we take additional time and push the due date, I think that's going to be not a big deal. Section 8.1 starts to get a little bit shorter, and we'll be in chapter 8, further applications of integration. We'll be looking at arc length, just measuring the length of a curve, surface areas of revolution, and other interesting things like hydrostatic force and centers of mass. Kind of exciting stuff. But first we have to get through section 7.8, finishing off our improper integrals. These are weird integrals, but they do come back in chapter 11 in different forms. So it's kind of a preview of what we'll be doing later. No worries, Michael, I understand. Other questions so far? Okay, well, let's see where we left off on section 7.8. We were on example 1 part B, looking at this integral. It's an improper integral for multiple reasons. It is an infinitely long interval on both ends. We're going from negative infinity to positive infinity. So we're integrating this thing on the entire real number line is what this is saying, and trying to get an answer out. If we look out on a graph on this thing, it looks like there really could be an answer. But notice this graph is kind of cherry picking. I'm looking at that interval right here, integrating from negative infinity to 0, x e to the x function. It looks like it should have an answer, and the answer should be negative. We, in fact, did calculate that one. The integral converges to -1. So the process was, we took this one, we broke it into 2 integrals, called it I1 plus I2. I1, because of the improper integral, negative infinity down here, we convert to a limit as t goes to negative infinity, and drop the variable t down. Next steps we took was we had to integrate this by parts, and those are the integration by parts steps. We evaluate from 0 to t on each one of these, so 0 to t here as well, and that's just the answer after we take the integral. Next steps we have to take were the limit. This one highlighted was tricky. We used L'Hopital rule. I don't think this came up in the homework, but this is more of a just kind of a review and a preview. L'Hopital's rule couldn't come up in chapter 11 in the homework. And we found when we came back to the limit, that part went to 0, this stays as -1, and e to the t goes to 0 as well. So our very first integral from -infinity to 0 converges to exactly the quantity -1. So we say the area of this curve, which goes to the left forever, never stopping, is -1 through that limit. But that's not the whole story. There's a whole lot more. Just more of a wrap up of what we've done so far. We were only looking at I1. We have to turn to I2 and see what happens to the second half before we give a total answer to this thing. We were only looking at half the problem essentially. So let me take a quick screenshot. We're looking at this portion here. And here's the second half of the problem. Really long problems. This is kind of unusual in the homework for these to be so long. There's not too many of them. But at Desmos, if we're looking at that thing, it means the picture looks like this now. If you saw that graph, what would you say? Does this converge or diverge? I agree with you. We're looking at the area under this red line, but that grows faster than an exponential due to the factor x on it. We don't expect to get an answer on this, but yet you have to demonstrate it really does diverge. That can be weird like that. Sometimes your intuition can just betray you entirely. So we're going through the motions. We know what we expect. By the way, it's always a good idea on these problems to just take another look using technology. So let's call this I2, inheriting the notation from up above, where we labeled it as I1 and I2. I2 is this one. Integrate from 0 to infinity, x e to the x dx. Okay, I'm done with that note there. Well, this one has a problem right here. This is what makes it an improper integral. We can't use the fundamental theorem of calculus at all in that format. So the required first step in the homework is to write this. Limit as t goes to infinity of the definite integral now from 0 to t, so t replaces the infinity, x e to the x dx. There's actually really good news once you get to this point. I mean, it feels kind of not nice of a problem because it looked like it took a long time just to get the first answer of -1. But notice what we can carry over. You don't really have to integrate that a second time. We can just take our work from right here and reuse it. The only thing that's changing is we're going to positive infinity, not negative infinity. And also these are flipped. It's going from t to 0, not 0 to t. So I encourage you to think in those terms. Don't reinvent the integration, reinventing the wheel. Use what you've already calculated. Oh, sorry, I missed that, Michael. Yes, absolutely. This one is diverging. So let me take a quick screenshot once again. We're going to grab that and just reuse some of that stuff. Let me just make this a little bit smaller. There we go. So here's what I would do on the next step. If you're just changing the direction you're going, a different integral with different upper limit to lower limit, you can now say that this is limit as t goes to infinity of, let's scoot down to that, x e to the x is going to be from 0 to t. So I'm just switching the integration or the limits of integration. You can copy that in, but we might as well go down to that step where the antiderivative is plugged in. Go minus e to the x. This one evaluated from t to 0. Let me promote these brackets here so this doesn't look too hard to read. So now we're pretty much done with that. But any questions so far, folks, to that step? Okay, so it's not always as long as a problem as it looks like, since you can take massive shortcuts after doing the integral I1, just apply that to integral I2. You still have to show the rest of this stuff, what's going to happen. So this is going to be limit as t goes off to infinity. Here's the evaluation with upper limit t. T times e to the power of t minus 0 using the lower limit. Then we go over here and we do it again. Minus e to the t to start, minus e to the 0 next. E to the 0 is just going to convert to a 1. And let's use this tried and true method of the problem continues on the next page. Hate to do that, but sometimes you just can't get away from it. So continuing on, it's now the limit. As t goes to infinity, probably what I would do here is start simplifying things. So we have t e to the t. Limits are tricky enough, not nice to look at it from this point of view until it's simplified, I'd say. Then minus e to the t, minus 1. So that's a little bit nicer to look at. Oh, sorry about that. Yeah, absolutely. Forgot to flip my negative sign. That's always kind of dicey with all the negative signs here. Thanks for spotting that one. So that should have been a positive 1 after distributing. Other questions at the moment? Okay, let's pause right here because this doesn't look good. T e to the t goes off to positive infinity. E to the t goes off to positive infinity. So this block right here is concerning. It's infinity minus infinity, and that is yet another indeterminate form. We can't get an answer from that view. But this is not a L'Hopital's rule problem. Still, I encourage you to take a look at these notes just as a refresher. Oh, my computer must have been updating. My mouse was lagging. These are the indeterminate forms we're concerned about, and we're on this case right here. Yet it's not a L'Hopital's rule problem because we can take a nice algebraic technique on this one. Just factor out e to the t, and it's much more easier to deal with. So this turns into limit as t goes to infinity of factored out e to the t, leaving t minus 1 plus 1. So now what happens in the limit? The exponential goes off to positive infinity times a linear function of positive slope that also goes off to positive infinity. That's a determinate form, infinity times infinity. That tells us this whole thing is infinity, and so I2 diverges. So that completes the limit. It completes a partial conclusion. We have a conclusion about I2, but now we have to say something about the original integral of the problem. Let's use this fancy symbol to say, therefore. We did a lot of work, so it seems warranted. All the work now says, therefore, the definite integral from negative to positive infinity of x e to the x dx. On one hand, if we restrict to just half the integral, we got an answer on this one. It was negative 1. But the other half diverges, so what would you say the overall answer should be then? Absolutely. If one part's damaged and it's diverged, the entire integral itself is now considered divergent. So we'll say here, this is, forgot the word this is divergent. Or you could just say diverges simply if you prefer. But we did it, folks. That's kind of the nastier kind of problems when we have to split it across two different integrals. And Michael asks, is that because an infinity can start from, for example, any number and go to infinity? That would mean there's no way to tell what it is. Are you referring to, say, like the infinity minus the infinity? Yeah, absolutely. Infinity minus infinity, it could come out to a positive infinity. This could be negative infinity, or it could be a finite number like pi, for example. So indeterminate form just means anything whatsoever can happen to this particular problem. Other questions about that so far? Yeah, absolutely. Thanks for that question there. These things are always pretty weird. And again, the reason we're kind of harping on indeterminate forms, not because it's a major part of the homework that we're going to be looking at, but it sometimes comes up in this case, even when you don't need L'Hopital's rule. And it also comes back in a pretty major way in chapter 11. We'll be taking quite a lot of limits in that chapter. So that one was kind of a nasty one, but we survived. In the homework set, I believe there's a couple along those lines. I forget the problems, but expect one that goes like that for a type 1 improper integral, and also for the type 2s we have yet to see. We'll see an example coming up on these notes. So what should we do next? Well, there's more examples. Here's the last example before we go to the different kinds of improper integrals. So we'll take a look at just an extra practice on this one. Probably needs a new page. Let's drop this down. By the way, when you see that integral, we know we're eventually going to have to get an antiderivative. Anyone see what the method is from chapter 7?
Could you do a partial fraction decomposition?
Yeah, good call, Brendan. If you see just a weird fraction and no available antiderivative, that's what it's going to be. Yeah, absolutely, Michael. So when we see the 1 over x, x plus 1, it's partial fractions. We might as well just get that out of the way. So I'm going to start with that. 1 over x, x plus 1. This is case 1 in partial fractions. And by the way, you might notice that when you go through this course, section 7.1 to section 7.5, those are the trickiest integrals that we're going to see. When you integrate further in the prior sections, chapter 8, chapter 9, and so on, they get a little bit more reduced in complexity because this is already a pretty large problem, the fact that it's improper integral. We're not trying to throw in a nasty antiderivative on top of that. So sometimes the integration is a little bit more streamlined in these kinds of sections for that reason. So this is going to break down to a over x plus b over x plus 1. Clear denominators, I think I always wrote this, so let's write this in again. Clearing denominators can be visualized this way. Times x plus 1 here. So I'm not sure what's going on with that highlighting. There we go. Times x plus 1 here. And then finally here. Not necessary to write that in, but I think it does help with visualizing what gets canceled, what's left over. On the left-hand side, just a 1. On the right-hand side, we get a times x plus 1 plus b times x. This one, I would use the method of just choosing values for x. This is a really fast one if we go with that method. Let's pick x is 0 to start. That solves for a. So if x is 0, our equation above implies 1 equals a. And we're done. That's one coefficient already, so it's pretty fast. Next, we pick a negative 1. X equals negative 1 implies 1 equals negative b. The first term cancels. We get negative b here. That one did involve another step. B equals negative 1. So now we have two values, and we can now convert our problem into integrating 1 over x minus 1 over x plus 1. It still has a bigger problem, though. It's an improper integral, so we have to handle that as well at the same time. Any questions at all, folks, with the partial fraction decomposition step? Okay, might as well just convey it up here. Now that we found the values, this is turning into 1 over x. And I almost put plus, but really minus 1 over x plus 1. So coming down below, this work then shows the improper integral, integrating from 1 to infinity of 1 over x plus 1 dx, turns into a limit. We have to replace the infinity symbol so we can actually use the fundamental theorem of calculus. So now it's limit as t goes to infinity. And the homework, this is a required step. It's not worth a ton of points, but you could lose a point on this problem, not for showing the limit right here. We have to use the proper notation and say what we mean what we say. And when we do this integral, this is literally what we mean. We're taking a limit as the upper limit of integration just gets larger and larger and larger, and seeing if this converges on some finite number. So 1 over x, here's the decomposition, minus 1 over x plus 1 now goes in. And here, the antiderivative is not so bad. These are both natural logarithms with those denominators for their input. So now it's a limit as t goes off to positive infinity of natural log absolute value of x minus the natural log of absolute value x plus 1. So all of that is going to be now evaluated from 1 to t. And I always feel like I didn't make those brackets big enough to show where all the brackets are going. That's kind of hard to read. I put x plus 1. Let me see if I can fix that. Looks like an 11. X plus 1, then close those absolute value bars. I think that's what I intended to write, went sideways there. So now we're taking this with the evaluation. And by the way, since t is going off to positive infinity, we can essentially drop the absolute value bars. The input here is going to be t, guaranteed to be a positive number. So continuing on, this is now limit as t goes off to infinity. On the upper limit of integration, we just get natural log t minus natural log of t plus 1. That's going to be a tricky limit for the same reasons we were talking before. We're looking at another indeterminate form. Oh, sorry, Michael, I missed that chat there. I need to be more careful with that. A little red button just appears right at the top of my Zoom controls. I have to see or else I'll miss it. For this one, I think it does converge to some weird number, but yeah, I think you're on the right track. This is a convergent integral. And there's a way you can guess that. If you look at this, it's kind of like 1 over x squared, right? It's just the x plus 1 factor that's throwing it off. 1 over x squared is special because of that right here. If you integrate 1 over x to a power, then if the power is larger than 1, we are expecting convergence. So thinking along those lines, it ought to be a convergent integral, but we have to show it. And even worse, if it converges, we have to say what it converges to. So, oh, not that far down. So definitely a lot of work to get through on this one. But other questions or comments so far? Okay, so I put in the upper limit t. Now let's go minus. I'll parenthesis just to make sure we don't have a sign error. Throwing in 1, we get natural log 1. We can drop absolute value bars. Minus natural log 1 plus 1, or natural log 2. Natural log 1 goes to 0, so that term is gone right here. It's kind of nice. And we're left with an awkward situation like before. As t goes to infinity, so does natural log t. So lim as t goes to infinity, natural log t, that is infinity. And same with this one. So this is indeterminate of type infinity minus infinity. We can't do much with that. And this one is still not necessarily L'Hopital's rule. Here's what we can do. We'll just use properties of logarithms. If you have a difference of logarithms, you can say natural log a minus natural log b is the natural logarithm of a divided by b. And then that would help us out a lot with this one here. So let's come down, write that this is limit as t goes to infinity of natural log t divided by t plus 1 through properties of logarithms. Here, this canceled out, and checking my double negatives, this turns into just plus natural log 2. That one's a constant here, so the convergence or divergence of this integral rests solely on what happens here in the limit. Now, here's where we're kind of just reviewing limits as we saw them in Calculus 1. Natural logarithm is a continuous function, and there are really cool properties with limits as it relates to continuity. Here's how it goes. We're going to take the limit of the first term where the red dot is, but the limit operator passes through the natural log due to continuity. It turns into the natural logarithm of the limit as t goes to infinity of t divided by t plus 1. So the limit affects it in that way. The limit just essentially went inside the natural logarithm function. Over here, that's a limit of a constant, totally unaffected. It would just be plus natural log 2. So we need to resolve that limit there. And that's why I have some review material on the notes here in Moodle. But while you're looking at it, anyone happen to know that limit? We'll definitely describe how it goes. It's 1, good call. The trick here is that's a rational function. We'll take a look at the review material. By the way, this is a limit that's going to come up all the time in chapter 11, so it really deserves a shortcut. Even in Calculus 1, people mentioned that this is a good shortcut to take if you see it. So let's take a look at the review documents. It's about section 2.6 is what we're concerned about. Oh dear, I should have done that. Hang on. There we go. Okay, so really focusing, let me get rid of that stuff down there. Focusing on that limit right here. Here's a review material that's going to help us out. Once I get my windows going, there we go. So we're looking at a limit as something is going off to infinity. And down here, we'll say that the line y equals L is a horizontal asymptote to your function if and only if the limit as you go off to infinity is the value of that asymptote. So what's kind of nice that means the moment you know this has a horizontal asymptote, you automatically know the limit as you go off to infinity here. So how do you find the horizontal asymptote? Well, if it's a rational function, you pull coefficients. There's a coefficient of 1 here, a coefficient of 1 here, and so that means because the degrees are the same to power 1, the limit of this is exactly 1. Let's just do a couple quick examples to kind of convey those thoughts. Let's say you're taking the limit as t goes to infinity of 3t minus 4 divided by 6t minus 8. Same situation. This is a rational function, and there's a tie, degree 1 above, degree 1 below. Even if it was cubed above and below, the fact that there's a tie means you grab coefficients. This would be a 3/6 or a 1/2 in the limit. So that's one case that could occur. Another case is lim t goes to infinity of 3t cubed minus 4 divided by, let's make it 6t power 4 minus 8. Anyone happen to know the limit in this situation? The trick to this one is if the denominator wins, even if it was t to the power 3.1, for example, then as t gets large, the fact that you're higher degree in the denominator becomes tremendous. This is what the graph would look like if we plot that thing. Let's go y equals 3t cubed minus 4 divided by 6t4 minus 8. We're concerned as we go to positive infinity, but check the second coordinates. Those are definitely going down to 0. And what's making it go down to 0 is specifically that power is higher in the denominator. In fact, put in 3.1, notice same kind of picture. You just have to move further and further to the right to make it go down by the same distance. So this one would have a limit of 0 immediately, and that's simply because of the power 4 being higher degree. So there's a third case. Let's take limit as t goes to infinity. Let's say it's something like 3t minus 4. Let's make it squared, divided by 6t minus 8. This one's like the opposite of the one above. This time we're higher degree in the numerator, and that means, well, the values of this are going to get larger and larger and larger, positive. So this one would come out to infinity. So it's kind of a weird side journey right here from Calculus 1. But this stuff right here, these kinds of limits, come up so often, especially Chapter 11, that we'll come back to these kinds of ideas and mention the shortcuts as well. The one thing you wouldn't want to do is take a whole lot of time doing these limits because the problems are already long enough on their own. So these are good shortcuts to take when we see them. Back to the problem, though. We're working this out. First, any questions whatsoever with that side discussion? Yeah. Oh, yeah, absolutely.
So if you just have an horizontal asymptote, that's what you're, and it's convergent, that's what the convergent equals.
Exactly, yeah. The moment you know your function has a horizontal asymptote, it's the value of the limit at infinity. So because of this one coming out as a 1, that's what's giving us a convergent on this one. However, if this diverged to infinity inside here, we would have said the whole thing diverges. So if there's a t squared right there by the red dot, in other words, the integral is divergent. But it looks like we're going back to what Michael Brown said. This looks convergent now because we get this as an output. It's now natural logarithm of 1 divided by 1, or just 1 if you prefer, but I'm just trying to show how we grabbed that value. It came from the coefficients, plus the natural log of 2. This is natural log 1, which is back to 0. So the whole thing turns into natural log 2, which means it's convergent. That means this number, or excuse me, this improper integral right here is like the world's most fancy way to write natural log 2. Kind of a weird thing, but the area under the curve is exactly that quantity. Is what all this work is saying. Well, any last questions, folks, with that example there? Okay, definitely pretty weird stuff. Improper integrals, again, I keep mentioning, this comes back in chapter 11. We'll see these kinds a lot, but there's a little bit more going on in these notes. These were improper integrals type 1, where you have an infinity on one end or the other, or both, for your limits of integration. But now we're going off to a different land of improper integrals. Here's the example that we discussed when we were discussing this before the exam. This one doesn't look like it's improper at first, because there's a finite domain we're integrating from -1 to +1 has length 2. But there's a bigger problem. You still cannot use the fundamental theorem of calculus on this thing because 1 over x is not continuous. We require a continuous function to use the fundamental theorem of calculus. And here's its problem. Plot 1 over x, you have an infinite discontinuity, which means there's a lot of work to be done on this kind of thing. So that's what makes it improper integral type 2. I think when you see type 2, it's referring to discontinuity. So now we're on the hunt for discontinuities for this second batch of problems. So in the section 7.8 homework, if you don't see an infinity on your integral, then that's a pretty big giveaway. It's a type 2 improper integral. There's a discontinuity somewhere. Now, it could happen anywhere. If f is continuous on this kind of domain, that means we're thinking of the discontinuity on the upper limit of integration b. We can fix that. We're using the same exact strategy as before. We take the b, you can't use it, it's a discontinuity of the function. And so we put in a variable t. Here's where it gets a little bit dicey though. Notice the limit is a single-sided limit. Why is that? Well, if you're from a to b, I'm looking at this domain here, just going to visualize it as a number line. The bracket, I'll put a solid dot to say we're actually using that value. But b, we cannot use. It's not continuous at b. This is the domain of integration. Your variable t goes from a to b. Let me fix that b, though. It looks like the number is 6. But that means when t gets closer to b, it's only approaching from the left. So we need that extra symbol there. T approaches b from the left. And we have that new integral to work out. The rest of the steps are almost entirely similar on that part. So that's why this is in this section. Improper integrals type 2, they start out different, but then you'll notice when you're doing the homework problems that the rest of the work feels very, very similar to what we were just doing. So that's one case that can happen, but your discontinuity could be over here. If your discontinuity is on the lower end, then we take that a, throw in a t, but we have to take the limit as t goes to a from the right now. Just to revisualize that, there's nothing wrong with the interval notation, but I think, at least in my brain, I think it makes more sense seeing it this way. Here's a, open circle due to the discontinuity. Here's where b is, solid just conveys, we can use that value. And your variable of integration in the limits right here lies in between. So that means when it's approaching a, it's always larger than a, so we say it's approaching from the right with that plus symbol. So these are the nice cases, but your discontinuity doesn't have to be at the end or the other end of your limits of integration. It could be right in the middle. So this is where we have to split in two, just like when we have negative infinity up to positive infinity. So if you have a discontinuity C in the middle, what you do is you take something like this. Here is A. Here's B. Here's the problem C right in the middle. We can integrate from here up to here up to here, but then what we do is we take the discontinuity at C and break into two different integrals. So the whole interval from A to B starts by going from A to C. The A to C you see right there is just this part. Then you break it up to the next integral, going from C to B. That's this other part right here. But you have to convert these into limits. So seeing what we did above, that's why you have t going to C from the left. On this one right here, your variable t would be in that location. So it's approaching C from below. But when you go over here, you move your t around. It's now over here. It's not approaching B. It's always going towards the discontinuity when we take the limit. But it's above C, so we approach it from the right using a positive sign there. So I always, when I do this personally, I always write out these little number lines because honestly, single side limits are tricky enough. Anything extra you could put down on paper to make it a bit easier to visualize is worth a ton, I'd say. So I'll get in the habit of doing that whenever we have this improper integral. Not required for you if you can see it a different way that works for you, but that's what you'll see on the notes quite a lot. Any questions at all, folks, with the rundown? Yeah. Oh, it's because the C value is where the actual discontinuity is. So say, for example, on this one right here, the discontinuity is at A. So we have to replace the A in that way. And same kind of issue here. Wherever C was, we replace it with, hang on, let me take another look at this. T approaches C from the left. Oh, I do have a typo on this. Thanks for spotting that. This should have been a C, or excuse me, a T right here on the upper end. Let me see if I can highlight that a little bit better. And I should have replaced this T right here on the lower end. Got so close, but didn't get to that last step. I'm glad you carried extra attention to that. Does that make sense on the corrections there? Okay, other questions so far?
On the limit as well, it would be t minus and t plus, right?
Let's see, yeah, so T minus on this one, if we're between, this was A and C right here. I see how I kind of mix that up on the notes. I need to look at this one to see how it comes down the limit. So yeah, this would be T approaches C from the left, so C minus with a superscript. On this one, T is between C and B, but it's going from the right, so it should be a plus. Other questions with that so far? Okay. Well, it's one thing to see how it goes on paper like this. It's actually pretty tricky to visualize, but I think it always comes together a little bit better once you go through an actual example. So let's give it a try. These are not the worst integration problems ever, but they all have big issues, things you wouldn't see in Calculus 1. For example, this integral is totally unfair in Calculus 1. If this was an exam 1 problem in Calculus 1, a lot of people would assume it's just a typo. Anyone see what the problem is with that function, that integram?
It goes to 1 over 0.
It does. In the upper limit of integration, if we use the fundamental theorem of calculus, we have a big problem. 1 is not in the domain of this thing. We have a discontinuity. So here's what we're going to do instead. Let's visualize a number line with the lower and upper limits of integration. We're going from 0 to 1. The solid dot means we have continuity there, and so does the highlighting. But the open circle is my way of conveying we have a discontinuity. Right at 1. Our variable t goes between those when we go to convert to a limit. And so this is what happens with this one. It's going to turn into the limit as t approaches the discontinuity, 1. But then what would you put here? Is this from the right or from the left? In other words, a plus or a minus? Any volunteers for over in Zoom? Is this a left
Minus.
side? Absolutely, good call. Left side limit because t is always below 1. So we have to approach in this direction. Minus going like that. Let me make that number a little bit easier to read. T approaches 1 from the left. So that means we go from 0 to t. So here's what we're doing. The discontinuity, kind of like the infinity in the prior problems, gets replaced by limit as t approaches it. And so now t is the upper limit of integration. You can't use fundamental theorem of calculus here due to the discontinuity, but you can here because t is assumed to never take the value of 1. We're just taking the limit as it approaches 1. So same thing inside is 1 over 1 minus x dx. Then from here on out, not so bad to get through. This is a little tricky in antiderivative because you have to think in terms of chain rule to make it work, but still not so bad. It's now limit. As t approaches 1 from the left, antiderivative of this is natural log of absolute value of 1 minus x. But then a little bit more goes here to make that totally correct. Exactly, good call. We need an extra negative sign inside there. Because if you differentiate this, 1 minus x goes down below, absolute values fall off. But then you multiply by the derivative of the 1 minus x, that's an extra negative sign. So we arrange that negative sign there to cancel it. So evaluate that all from 0 to t. And here's our next stage. It's now the limit. T is approaching 1, coming in from the left of all of this stuff. Let's first do something with that negative. I think the best thing to do with that is to avoid all the multiple double negatives that could occur. Just take this. It's a constant -1. You can move it in front of the limit. Just a little bit easier to deal with going that route. Next, I'm going to place a t here. So natural log absolute value 1 minus t. We can drop absolute value bars at this step if we like, because t is always less than 1, which means 1 minus t is always a positive quantity. Plug in 0 and we get minus natural log absolute value of 1. That kind of just keeps on coming up. So you might have noticed that really good shortcuts with logarithms and a lot of problems in the book, the ones I bring to class as well, are natural log 1 is also always 0, natural log e is always 1. So now we're taking the limit of this stuff. And this is a pretty tricky limit to take a look at, I'd say. But first, let's simplify it just a little bit more. This is negative lim. T goes to 1 from the left of natural log 1 minus t minus 0. So all we have to focus on is that right there. Well, to do that limit, we should know what this limit is. Anyone happen to know what the limit of t approaches 0 from the right of natural log t should come out as? It is, good call. This limit is -infinity for any logarithm, not just the natural logarithm. Reason being is this one has a vertical asymptote. It goes like this. Goes through 1 on the x-axis. And it gently increases to a positive infinity, very, very gradually, but it gets there. However, on the left end, it's plunging. Notice that's why I need 0 from the right here to make this work out. And so let's look at what happens here. As t approaches -1, I don't think I want that. Actually, let me use this temporary ray to highlight it. As t approaches -1 from the left, we get values here that are getting closer and closer to 0, in fact. We get, say, for example, 1 minus 0.5, then 1 minus 0.7, 1 minus 0.9, 1 minus 0.999, and so on. If that's getting closer and closer to 0, we're really doing this limit. We're putting in values that are getting larger and larger negative for the outputs. And that means this whole thing is divergent. That part goes to -infinity, but we have an extra negative sign, so the whole thing is positive infinity for a divergent. integral on this one. Looks like it could have had an answer. It was looking great so far, but that limit as t approaches 1 is what did it in for diverging. Any questions at all, folks, on what happened with this thing? Okay, and again, with a lot of these kinds of problems, when you're doing them in the homework, you can get a good sense of, is this even right? A good intuition on this, kind of a partial check, by just simply plotting the function. So let's take a quick look just to illustrate that. We won't do it for every single one, but this is our first improper type 2, so we might as well. Let's return to the original range. The function goes y equals 1 over 1 minus x. We need a specific domain from 0 to 1, so let's put that in. 0 less than or equal to x. Strictly less than 1, that's a discontinuity. And this is the graph. Doesn't look good. We're looking for the area under this graph. And what we said is, area under this graph must be positive infinity. Looks about right because, well, that's a vertical asymptote right at positive 1, but it looks like it wouldn't approach that vertical asymptote fast enough for a convergent area this time. Well, that's the story of this one here. We have a couple more to take a look at, but any questions or comments so far? Okay, so let's take a look, change gears and take a look at part B. Well, we are doing a definite integral from 0 to e of natural log x. And I guess we have this open already. Let's take a look at this. We're going from 0 to e. The function is natural log x. And so our question for ourselves is, what about this one? Notice the curve hits the x-axis really pretty rapidly this time. There's finite area in this region, so no trouble there. We have negative area and positive area. Would you say this converges or diverges just based off the picture, the graph itself? Not sure is a very valid answer, because this could be really kind of tricky. Michael says converges over chat. And I do believe you're right. I practiced this one earlier. It's the only reason I know. Really hard to tell just by the graph, but convergent looks like it's right for this because this negative area doesn't seem like much when the curve approaches the vertical asymptote so rapidly this time. So we're back to that picture of natural log x, stopping at e, but here's the domain once again. From 0 to e is not the problem. Natural log e is 1, no trouble there. You cannot calculate natural log 0 using real numbers. So this is the discontinuity. All right, DISC, just shorthand for discontinuity. So t is somewhere in this range from 0 to e. That means we're approaching 0 from the right. So this whole thing now converts to limit. T approaches 0 from the right. T goes into that position, e up here, and now it's natural log x dx. So that was our discontinuity right here. We replace it with that limit statement there. Any questions, folks, with that first step? Okay, well, on this problem, once we get to this stage, we need a good antiderivative. However, this is an antiderivative you can take for granted by formula. Natural log x dx. You can integrate by parts on this one, but I'll leave it up to the class. Should we integrate by parts, or does anyone happen to know the formula? How about parts? That'd be a good review problem. So good relaxing integration by parts. Let's work this out. If you're integrating by parts, you'd probably be using this thing. And all we've got here is a logarithm. So, I mean, that's a natural choice to start. U equals natural log x. dv is left with just dx then from the integral. Differential of u, du is 1 over x. dx. Antiderivative of essentially a 1 turns into an x. So this thing becomes uv minus the integral of v du. So first u times v, that's natural log x times x. I think it's better written x natural log x minus the integral of v times du. That would be taking x times 1 over x dx. That's just 1 again. Antiderivative of 1 we did already up here and got an x. So this turns into x natural log x minus x plus a constant. But just to re-emphasize, this is a formula you are welcome to take for granted. What I mean by that is when this comes up, you may use the formula. The one right here, x natural log x minus x. Reason for that is antiderivative of natural log x, it comes up a lot. So doing integration by parts like 12 different times in this course, every time it occurs, it just feels super tedious after a while. So you're naturally just going to want to put in the answer after you've done it a few times. Well, let's do just that. Let's put in the answer over here. So we're taking now the limit. T is going to 0 from the right. Put in a big bracket this time. Here's the antiderivative of natural log x. So x natural log x minus x. But all of that is evaluated from e to t. Close the brackets, and now we're one step off, or one step further, rather. Let's put in the evaluations next. We have the limit as t goes to 0 from the right of plugging in e gives us e natural log e minus e. Plugging in t gives us t natural log t minus t. And let me just move that arrow over. So now we're just about there. We need to work all this out. Simplifying it next gives us limit t goes to 0 from the right of natural log e is a 1. So this just turns into e minus e. Not so bad. Minus t natural log t plus t. So that's our limit to take right here. So some parts of this limit are not so bad. Other parts are worse. Cleaning it up a little bit more, it settles down as limit as t goes to 0 from the right of negative t natural log t plus t. Let me try to fix my t's. So this one is not indeterminate form necessarily what we're looking at, because, well, as we go from 0 on the right, that thing just goes to 0, it's gone. So that's kind of a nice limit. The struggle on this problem is this right here. What happens to that thing as you go to 0 from the right? Well, it's going to turn into that part goes to 0, multiplied, limit as you go to 0 from the right of natural log t, that's negative infinity. Let's double check. I believe that's indeterminate, but this document here is always really good for a double check on that. If you get 0 times an infinity, we're now indeterminate again. Reason being is 0 times infinity can do anything. If t goes to 0 fast enough, the whole thing is 0. But if natural log t goes to negative infinity fast enough, the whole answer is negative infinity. And yet, there could be a compromise. It could settle on a finite number, like 5, 12, negative 2, who knows? We have to work this out through L'Hopital's rule. So what we'll do is, we'll call this L, come back to it. This is indeterminate. And now we're just going to do a mini limit review problem. Again, this doesn't come up in the homework from what I saw, but it will come up a good amount in chapter 11. So it's kind of a review and a preview all in one. I'm going to ignore the negative sign since that's not going to determine whether the limit exists or not. It's all going to be about the functions, t natural log t. If that converges to a nice finite limit, we'll bring back that negative sign. So at the moment, I'm most concerned about limit. T goes to 0 from the right, t natural log t. it's this type of indeterminate form. You can't use L'Hopital's rule until it's infinity over infinity or 0 over 0. So we send one factor down into the denominator. I wouldn't do that to natural log t, though. That's a complicated function. If you put a power -1 on it, you now need a chain rule to work that out. But sending t down to the denominator is kind of routine business. We do that all the time. It's much easier and easier to differentiate. This will be limit. T goes to 0 from the right of natural log t, divide by t to the power -1. Once we do this, we have to analyze what's going on again. Natural log t still goes to -infinity, but the t power -1, that's a function y equals 1 over t. Graph, well, the right end of the graph that we're looking at goes like this. So if we go to 0 from the right of t power -1 or 1 over t, that's shooting up towards positive infinity. But that's good news. It's still indeterminate, but L'Hopital's rule will now work on that indeterminate form. So we're indeterminate here, still indeterminate. But now we'll put an h here because we're using L'Hopital's rule. There'll be limit t goes to 0 from the right once again. The numerator, derivative of natural log t, becomes 1 over t. In the denominator, derivative of t -1 becomes -t power -2. And we wouldn't want to analyze what kind of indeterminate form that is at the moment. Always simplify the algebra first so that it doesn't turn into some kind of wild goose chase. So on the margin, this is going to be, that's going to be hard to show up. Let me try using just this usual scratch work pen. This is 1 over t, divide by -1 over t squared after correcting the negative exponent. So it's -1 over t times t squared over 1. Which means the whole thing is just a -t in total. So ordinary equal sign, we didn't do anything but algebra. We have negative limit as t goes to 0 from the right of t. I just put the negative sign up in front. So we took something that is, well, totally mysterious. Anything can happen. Honestly, my gut instinct when I see that is, it's 0, it's gotta be. Anything times 0 is 0 is our mantra in algebra. But not true in calculus if that's infinity. It's not even a number now. So arithmetic is out the window. We resolve it by the limit, and we find out that this is, in fact, 0. So our intuition is right. Kind of unfortunate when you do a whole bunch of steps just to confirm what your guess was. But this is truly indeterminate. It could have really been anything. So going back to the limit, well, first, any questions, folks, with the side journey on L'Hopital's rule? Yeah, absolutely. The one for ln x goes like this. It intersects right at 1 on the x-axis and goes about like that. This is misleading. No horizontal asymptote. The natural logarithm just increases incredibly slowly, the reverse of how an exponential increases extremely rapidly. But that's where we're getting the -infinity when we go to 0 from the right. Other questions so far? Okay, well, let's put it all together. I wrote equals L just so that we could come back and connect the dots. Now we're going to say L equals, by the way, L through all these inequalities is the original integral up here. This portion in blue turns into, well, let me just first write it in so we know what we're connecting. Now that t goes to 0 from the right of -t natural log t. Scroll up so we can hide that problem. Plus t. This whole thing turns into 0 plus 0, which means it's 0. This whole thing converges. Kind of a surprise on this one. And we look at the graph one more time. Maybe not a huge surprise, right? Because this is positive area. That's negative area. The shape is different, but that's a vertical asymptote. Area keeps on going forever downwards. It turns out there's a balance here. That negative area is exactly the positive area. And so that's why the total integral converges to 0 this time. So just in other words, just to reconvey what we said here, let's just put a big overall conclusion. If you integrate from 0 to e of natural log t, that is a bizarre integral. First off, it's improper. You would never look at this in Calculus 1. But with more tools with limits, more ideas with integration, we found it's 0 and it's convergent. So pretty weird stuff. Any questions though, folks, on getting through these so far? Okay, I have one more on the notes to take a look at, but we have about 6 minutes and some change. So we're mostly going to look at it and say, what would you say the problem is with this one? We're integrating from 0. You can plug a 0 in there. That's continuous at x equals 0. We're going up to 2. You can plug 2 inside there. The function 1 over x cubed, by the way, red because this is a revision. My last function had a domain error. It did not make sense. So this is a better problem. Exactly. Our discontinuity is in the middle. This is the type of problem we split into 2 integrals, and we have to look at each independent piece. If they both converge, we'll have a total answer. If just one diverges, the whole thing is going to be a divergent problem. So we need to split this one up. But this might be a good one to come back to. I would hate to rush through this problem in about now 5 minutes and some change. But any questions at all, folks, with what we've done so far today? Or this one right here? Okay, well, we'll reconvene on Thursday's class, finish off this last problem. We'll take our time with it. It's a tricky one, I'd say. And then we'll be officially in chapter 8. So congratulations, we're through the first chapter. In a calculus class, whether it's calculus 1, 2, or 3, there's a pattern here. Usually the first chapter is the hardest one to get through. In calculus 1, it's limits. That's just brand new and crazy. In calculus 2, it's crazy integration techniques that you have to hit the ground running on. And in calculus 3, well, you're doing everything in multiple dimensions, so you have to do some linear algebra really to get started. So chapter 8 is where it starts to cool down a little bit, and people start getting caught up most often in these kind of classes. So we're over the hump, essentially, getting through this section. Well, have a great night, folks. Drive safe, stay dry, and I'll see you all in Thursday's class. Sure. There is a director of tutoring, and another person was just asking about that. There's a weird problem going on where the director of tutoring at ISU manages everybody who deals with tutoring. He's moving to a different position. This is terrible because it means they're hiring a new person and everybody's dropping the ball. Sorry about that, but I can get you in direct contact with them if you like.
Well, my problem was that when I applied to tutoring, they just said that the tutoring center was full.
Not down here. They're mixed
That's
up.
what I
Yeah,
thought.
they have no idea what's going on.
Okay.
Yeah, if you like, you could reach out to them again, or I could reach out on your behalf. Up to you.
If you could give me contact information and if you would also.
Yeah, absolutely. So let me give you that
send
contact.
something about
Yeah, and it's Steve or Gavin, right?
either.
Gotcha. So this is a reminder for me to reach out to Doug. Yeah, another person was wanting to tutor for our tutoring center, same exact problem. It's kind of depressing in all honesty, but let me give you his contact information next. So our director, who's getting a promotion, but should be still doing his job, his name is Doug McGee. And let me get his email address next. I'm not good at doing this on a phone. Let me try again. Okay, I've got him. Okay, click on his face, and there it is. Actually, it's email. Okay, so here's this information. Again, sorry about that. ISU is really failing on that front, I'd say, just dropping the ball in tutoring entirely. We definitely need people on this campus to help out. I don't know if it's a problem that they're saying that they're running out of money to hire tutoring people, but based on what you said, they're just confused as
Yeah,
hell.
they
is what it
just told
sounds
me
like.
that they were full, and I was definitely sure I was applying to this campus.
Yeah, they're getting really screwed up there. Hopefully they get it settled out somehow. Sorry about that. Yeah, you bet. Any questions?
I had a little quick one on 7.7.
Sure.
So on the end there, I got 18 off of this graph instead of the 18 and 6 repeating. I was just wondering if that was fine. with you.
Absolutely,
Okay.
yeah.
'Cause
For
I'm-
these kind of problems, there's a big fudge factor for sure.
Yeah, cause I'm just like, I got the 18, but I'm just like, he got this one, I didn't, so I don't know.
Yeah, I might estimate something slightly differently, but yeah, that'd be just fine for that one.
I was wondering.
Cool.
Yeah, I'll skip this one.
Sweet, you're super caught up then at this point. That's awesome.
This one, I'm glad there's only 4 questions.
Yeah, a little bit more manageable.
Yeah, that helped.